Okay, well, let's go ahead and get started. So good morning and welcome to this opening Forum 360 session, which is going to focus on CREATE. And the title of this session, as you can see, is CREATE, Enabling Innovation Through Computational Prototypes and Supercomputers. So I'm Paul Nielsen, the Director and CEO of Carnegie Mellon University's Software Engineering Institute, which is a DoD federally funded research and development center, sort of like Mark Lewis, who was on the opening session today. Although I'm more of a manager now, at my start of my career, I was a computational plasma physicist. So modeling in sim, using high-speed computers to do a lot of scientific investigation is really near and dear to my heart. As many of you know, CREATE is an effort of the DoD High-Performance Computer Modernization Program. And that's always a mouthful to say, but it's an important program that's been around for quite some time. In its early days, the program primarily concentrated on the hardware side of this, on providing high-performance computer assets to the Department of Defense at various sites around the country through all the services, and making that freely available for researchers to use. About a decade ago, though, the program began to work on creating software that could really take advantage of both the architecture and the throughput and other capabilities of these high-performance computers. And that's really what started the CREATE program. And we all deserve some debt of gratitude to Doug Post, who's sitting here, for being on the plus side, you could say the person who had the initiative to start this. On the negative side, you could say the person who was irritating enough to make this happen, because it took a little bit of that to make this happen inside the Department of Defense. And now this program has been around, as I said, for about 10 years. It started to have some real impact and continuing to expand its impact throughout the Department of Defense and the defense industrial base. And that's the real important thing, because while there's tremendous scientific bases for these software programs and codes, the most important thing is that these are verified, that they're out there, and that they're being used to take advantage of high-speed computing in a very integrative way. So we have a distinguished panel here of 6 experts, 3 from the High Performance Computer Modernization Program Office, and 3 from the broader community of people who actually use the code, which is really good. We'll hear from each of them, and then hopefully, you know how these sessions go, but hopefully we'll have some time for some quick Q&A at the end. And as you know, we have this nice way of doing the questions and answers that you submit them online through your browser, and then they pop up and I'll get to see the questions that are coming in. So I'm going to take a brief moment to introduce each of the people that are going to be speaking, say a little bit about them, so that as we go to the speech, we'll have a continuous flow of the work that's going to be presented. So first here we have Doug Post. Doug, why don't you just wave your hand so people can see who you are. He leads the CREATE program, a program, as I mentioned, he established about a decade ago. Doug serves in the High Performance Computer Modernization Program Office under IPA, Intergovernmental Personnel Act agreement with my organization, the Software Engineering Institute at Carnegie Mellon University. Doug received his PhD from Stanford University and spent much of his time in the Department of Energy programs, having served at the Princeton Plasma Physics Lab, Lawrence Livermore National Lab, and Los Alamos. Doug is a fellow of the American Nuclear Society, that's one we don't always hear of in AIAA, the American Physical Society, and the IEEE. And as I mentioned, we all owe him a tremendous debt of gratitude for his hard work in creating and nurturing CREATE. Next to Doug is Dr. Bob Meekin. Bob, yeah. He's the manager of the air vehicles component of the CREATE program. There's 5 components under CREATE, and we're going to be concentrating on the air vehicle side today. The air vehicles part of CREATE has 3 major products that you'll be hearing about: Da Vinci, Helios, and Kestrel. And Bob will describe these in his presentation and give you some insight into each of them. Bob is a professor at University of Alabama, Birmingham, and supports the HPCMP, High Performance Computer Modernization Program, through an Intergovernmental Personnel Act agreement. Bob got his PhD in civil engineering from Stanford also, and has worked at NASA and Army research centers throughout his career, and he's an associate fellow of AIAA. Next to him is Scott Morton. Scott, just wave your hand, make sure people see who you are. Scott is the principal software developer for Kestrel, the fixed-wing aircraft product of CREATE. Scott leads 13 software and domain experts who are building a production quality tool that integrates this physics-based modeling and sim of aerodynamics, structures, propulsion, and stores and cargo separation into a single tool, single integrated tool running on these petaflop class machines. And I think the thing that CREATE has really brought to the table new is this integration of propulsion and aerodynamics and structure into one tool. As we've designed our propulsion systems to be more integrated with our structures now, this is really critical and has been a real challenge to people. Scott completed his PhD at the Air Force Institute of Technology and had a 20-year Air Force career before joining the High Performance Computer Modernization Program Office. And this had included tours at the Air Force Academy as instructor, at AFRL, the Air Force Research Lab, and at the Air Force Flight Test Center. And Scott's an associate fellow of AIAA. Next to Scott is Dr. Brian Smith from Lockheed Martin. Brian has 29 years of experience in the development and application of CFD tools, models, turbulence models, active flow, and aero optics analysis. For 5 years before he started working on this project, Brian was the chief engineer for DARPA's Aero Adaptive Aero Optics Beam Control Program, which developed and applied advanced flow control to design and test a directed energy turret. And you know, there's lots of special challenges of propagating that beam through good quality air, making sure you understand what you're doing, as well as take account of all the flows around the turret. Brian is an AIAA fellow and actually was in the class of 2016. I guess just about a year ago you heard about this, so congratulations, Brian. Next to him is Dr. Robert Narducci, who's a technical fellow at Boeing. Bob is a computational fluid dynamicist, leads their group on rotorcraft, and so we're going to hear a little bit about the rotorcraft side of things as well. He also serves as a CFD tech advisor to the Boeing enterprise, so you know, kind of helping people throughout Boeing, especially in the defense, space, and security sectors of Boeing's work. Bob is a Hokie, having completed his bachelor's and PhD at Virginia Tech. So we got a nice variety of people here and their backgrounds. And then finally, we have Dr. Ed Kraft, a long-term friend. Ed is a SES and a tech advisor at the Arnold Engineering Development Center, AEDC. Ed's worked at AEDC and AEDC support contractors for a long time. I think, if I looked up right, it's almost 50 years. Mm-hmm. Holy cow. How'd you do that, and yet you're only like 53?
Well, I talked to the Wright brothers, and they said it was okay.
Yeah. So Ed completed his undergraduate degree at the University of Cincinnati in aeronautical engineering, and then got his graduate degrees at the University of Tennessee. Ed's a fellow of AEDC and a fellow of AIAA. So with these brief introductions, I think it's time to get started, and you'll see there's a wealth of information. Another thing to understand is that this is the tip of the iceberg on CREATE and the tip of the iceberg on CREATE at this conference, because there are sessions on CREATE all day today, Tuesday, I guess not Tuesday, but Wednesday and Thursday, and I think maybe even one on Friday. So I think there's 25 or 30 sessions on CREATE in this conference. So look in your program. If you see some things in this opening sort of teaser that you like, you can dig a lot deeper during the conference. I'll turn it over to you, Doug.
Thank you. I'd like to, there's more information out there on the chairs or tables as you came in. One that's a brochure that describes the CREATE program. Presentations at this meeting, the papers that are being delivered, it's a schedule, so you can find it on Thursday at some place. And then there's a general brochure about CREATE there as well. whoops. Okay, so CREATE is about innovation. The goal is innovation. And listening to the talk this morning, I've decided to say a few words about what I think innovation really amounts to. It's really a disruptive change. And one of the key element that was mentioned this morning, and I look at what we're bringing to the table, is the ability to take a systems approach, to put together many different aspects of a problem and put them together in an integrated fashion and proceed forward. In the case of CREATE, really those multi-physics aspects are the airflow, or the fluid flow, CFD, the structural mechanics, which is the response to the frame, the ability to control the motion of the platform, the ability to have some way of sensing the environment, and the ability to the ability to put propulsion into the system. And this is important for airplanes, it's important for ships, it's important for ground vehicles. Okay, I'm part of the modernization program, the High Performance Computing Modernization Program, which provides a computing ecosystem for this. This consists of sets of computers, high-performance computers, supercomputers. We have roughly 15 large computers at 5 different locations, a total computing capability of about 30 petaflops, which is quite a lot of computing capability. They're linked together with a network, the Defense Engineering Research Network. That's located it's spread around, it connects sort of 300 users together to the computer systems. And then the third leg of this is software. We provide a lot of different kinds of software for the users, for the S&T and T&E community primarily. But as Paul mentioned, in 2005 I joined the program and looked around. I decided there was a tremendous opportunity, partially based on my experience in the Department of Energy laboratories, which were using supercomputers to solve their important problems. And so the Defense Department's not doing this. It can, and it has a lot of areas where we can really do better. The last 3 airplanes we built took over 20 years between startup project and initial operational capability. We can do better with supercomputers, and that's what I'm going to talk about. That's what this is about. So it creates a set of engineering tools based on high-performance computing, which enable us to innovate. What do you need to do to innovate? Well, you need to generate lots of options. You need to look at them and be able to analyze their performance, discard the ones that don't work, take some lessons from those, and reiterate and get some more and do this. So you can do the thing that was mentioned this morning about fail early and often. You can fail if you're doing it virtually and you're not putting it into hardware. And in fact, we're finding that in some of the areas we're able to generate thousands to hundreds of thousands of different design options. Look at the ones that really look like they're really going to work and throw the rest of them away. Take the lessons learned from the ones that don't work, and then develop narrow down to some really good options that we can then hit with the high fidelity codes, do a virtual test, and in a matter of months we can breadboard an entire new design of a system rather than taking years and years. It takes a long time to do an airplane. It also takes a long time to do a ship. And if you get a ship coming out of the States, it's taken 10 to 15 years to come together and to get built, and you discover a major engineering design problem, you're kind of cooked. So it's better to fail and to fail often with virtual systems. So with these tools, you can generate digital prototypes, and for ground vehicles and for antennas and ships and air vehicles. Okay, they also provide the ability to calculate the performance in actual environments. The ground vehicles part of the program is able to use terrain data to see how they go. The tools are government-owned and government-developed and government-supported, so they're available for the government to use to assess contractor deliverables, rather than just taking what the contractors show up with as their best guess, their best estimate, best effort. They're designed for a 30 to 40-year life. The software engineering is really of good quality, and now they're really being used extensively. Last count, 164 engineering organizations in the Department of Defense are using these tools. We have over 800 active software licenses, some of which are just one license for a large company. As Paul mentioned, there are a lot of different tools. There are 11 multi-physics tools, in the area of our air vehicles. You'll hear more about the air vehicles. In ships, we have a rapid design tool. We have tools to calculate the hydrodynamic performance, which is the core competency of the Navy, to calculate the shock vulnerability of ships, and to provide access to the different tools to the naval architects. And we have a good tool for computational electromagnetics that can do design of antennas, including co-site interference issues. Ground vehicles, I mentioned that. That project has just been started, and it's doing very well. And we have a way of generating the meshes and geometries for those tools. We supplement, the way we look at it, we supplement physical tests with computational analysis. In the past, one would put together a design based on the requirements of the Pentagon, make a real prototype, test it in the labs, test it in the test facilities, learn the lessons, go back and re-engineer it, and then eventually you end up with a full-scale system, and then you test it. If you have a problem there's not a lot you can do. Now we can replace this with, supplement this with an ability to generate a virtual prototype, and then test it with the high-fidelity codes and figure out what works, find the defects early, and fix them before you cut metal. We also put a lot of effort into building the software the right way with a long life. The software is built by government-led teams. There's about 50% government, 50% support contractors involved in this. They're embedded in the customer organization, so they're tied to what the Defense Department needs. There's a strong emphasis on software quality, verification, validation. I think the key part of success is having annual releases. Every year we release a new version of the code with increased capability. The versions are extensively tested, a rigorous verification and validation process. They scale better, they're more usable because we've gotten feedback from the users. That's enabled us to be responsive to changing user requirements, and they're extensively documented. Down in that little, down in the little, there's a chart of when the releases come out. You can see we just about every year meet it. We stagger a little bit, but it's still working very well. We have these groups. There's about 30 groups involved in this, spread across the country, and the groups are very closely coordinated. It's about 180 staff on the CREATE payroll, and roughly another 40% more of the people are put in from the services. We're impacting real programs. This is just a collection of those programs. For instance, we're doing the hydrodynamic design of the Ohio replacement ballistic submarine, shock analysis of the Navy's newest carrier, the Gerald R. Ford. We're getting flight certification data for the F-18 as it takes off and lands from carriers out in the sea under different weather conditions. Working with Boeing to help assess the advanced rotor blade retrofit that's going on to improve and get more lift, and store separation for the B-52. We're going into the future. We're going to continue the CREATE effort, but we're going to be looking at putting hypersonics into Kestrel, enlarging the capability of the ship's programs to do submarines, working more with the Joint Heavy Lift, the Joint Multi-Role Technology Demonstrator program to help it succeed, and many other issues that as we move along. The contact information is up here. You can go to the website for the mod program, just www.hpc.mil or create@hpc.mil, and we'll respond if you want to access. These codes are available to anybody who has a DoD contract, and we're willing to talk to other people as well. So to get access to these codes, you just have to give us a call, contact us, and we'll work on this. This also has the contact information for the rest of the CREATE program project managers and our operations officer, Mr. Scott Sunt, retired Navy captain. So,
Thank you, Doug.
okay.
So we're going to move over to Bob now, I think, right?
Okay.
It's a pleasure to be here with you at this Forum 360. I look forward to participating in the sessions for the rest of the week. So what I'd like to do is just give a very high overview of the air vehicles component of the High Performance Computing Modernization Program Office's CREATE program. So what we're trying to accomplish here, as Doug described, is to enable a change in paradigm. A change in a paradigm historically that's based on physical testing to drive design iterations to one in which the design iteration is driven by multidisciplinary physics-based simulation, and then have those designs validated by physical test. I'd like to clearly state that we're not arguing to replace physical testing with physics-based simulation. It's the intelligent and effective use of both of those to overall provide positive benefit to design and acquisition. So the advantages that we see in doing this are multiple. We can, through physics-based simulation, have an opportunity to detect design faults and anomalies early, prior to key decision points and prior to fabrication of test articles and full-scale prototypes. We have the ability through these, through high-performance computers and the coupled multi-physics simulation tools to assess planned and operational use scenarios and assess early how maintainable will these systems be once acquired and put into the fleets. We can plan and rehearse wind tunnel and full-scale flight tests in advance, getting more bang for our precious physical test dollars. We can contribute positively to the spectrum of sustainment phase processes and certifications. You know, in using physics-based sim in the design process, the design iterations early on, you know, we don't have complete descriptions of the designs, nor do we apply the highest fidelity prediction tools. So we design and analyze, and as we converge to more and more promising designs, the designs themselves become more complete in terms of systems and geometric descriptions and performance requirements. And as the designs become more complete, our physics can be also more complete. And when we get to the point of validating the design with physical tests, where there are differences between the physical tests and the predictions, we have the ability to add more physics and look at, well, what did we miss? What physics are missing, and add that, and then continue with the convergence of the design process. So when we're done, by the time we get to building scale models and full-scale prototypes, we have a really sophisticated digital representation of the weapon system, the aircraft, which persists through the life of the aircraft, so that we can handle block upgrades, and we have special ops new missions that weren't contemplated when the aircraft was designed and put into service. We can test those virtually. So we see just so much power in all of this. Next chart. Oops. Now can I go back? Okay. So what we're trying to do is change a paradigm again. And I think when I made this chart, I had some thought as to why red, why blue, and I don't remember what that was, so just ignore the change in colors there. All of the organizations represented on this chart are important, have important roles in defense acquisition. And so I want to call out just a couple of them in particular. First of all, the DoD program executive offices own the acquisition of these programs for for all practical purposes, the life of the system from concept through sustainment. The PEOs, though, they are consumers of data, and so you know, at least a willingness to consume physics-based sim data in addition to all other types is a requirement. But they're important. They look to the system manufacturers as well as the engineering organizations of the services in terms of making acquisition decisions. Now, since the engineering orgs and the system manufacturers are the generators of the data, these are critical. To change a paradigm, it's essential that the manufacturers as well as the engineering organizations of the services, accept the paradigm. And I'm not trying to imply that it isn't accepted today, but certainly it's pockets of acceptance and maybe limited to some disciplines. But to have a take fully advantage of the paradigm adoption is really essential. So that first little tick mark in blue, effectively drive the design cycle, reducing the number of design iterations and reducing the time from concept to deployment of a system. It's essential there. But also to effectively enable communication between DoD and the system manufacturers. It's critical that they both be able to talk toe-to-toe technically in engineering terms about the system attributes. So an adoption by both communities is essential. It's I think, important really that we recognize the role of academia in changing a paradigm. Academia is the source of all of our engineers in all of the defense engineering organizations, the research labs, all of the engineers in the system manufacturing organizations, all of the future faculty training or future generations of engineers. If we can focus on academia and getting at least limited capability versions of these tools, as well as tools external to CREATE, kind of promulgated and fully integrated within undergraduate, graduate education, research, both physics discovery and algorithm development. This is a huge impact. A relatively small number of graduating classes, basically we can take over the risk board, we can take over the world in terms of changing the paradigm. So academia has really got a critical role in all of this. And then I'd just like to point out the role of FAA for commercial, but also the DoD equivalent, those warrant holders and decision authorities for airworthiness are key to be willing to accept physics-based engineering generated data. This is not to say that it's not used, because it is, but current processes and constructs is that it's kind of a one-off time every time and has to be repeated, and when people retire or change positions, you have to, it's kind of person dependent as well as to how accepting they'll be of this class of data. And so real work needs to go in here to have processes where validated tools and processes can be used to complement, replace, work together with, fill in missing gaps in data that have traditionally been the area of physical testing. So what has the HPC Modernization Program Office and CREATE done to help enable such a paradigm change? The HPCMP has provided continuous modernization of HPC systems, the Defense Shared Resource Centers, and the networks that connect them, DREN. It's a very significant contribution. Then the air vehicles component of CREATE is providing multidisciplinary physics-based simulation software. We're continuously modernizing capabilities in response to prioritized needs of the services. We have a dedicated quality assurance group. We provide independent testing of all of our software prior to release outside of CREATE. We do rigorous V&V, and we provide tech support through our quality assurance group. We are trying our best to enable manufacturers to get an opportunity to preview the capabilities as they come out. We've awarded BAA contracts asking industry to look at capabilities coming out in Kestrel and Helios and DaVinci in the future and provide their feedback. We recognize that even if we provide the volumes of V&V data that we have for each of our tools to the manufacturers or anybody else for that matter, your corporate reputations, personal reputations are at stake. And before anyone adopts a new technology, a new tool, they are going to have to convince themselves that they do provide the right answers. So they'll take them to their own gold data and test and validate it. Yep, this is doing the job. This does provide the impacts and advantages that are being promised. And so through the BAA contracts, that allows the manufacturers to have a look, try it out on tools on problems that they care about, and then what we get out of this is we get feedback from important members of the defense acquisition community. We are able to factor that back into future releases of our tools, which is critically important. For the stakeholders within DoD proper, the engineering orgs, we do what we call STAR projects, strategically targeted projects, where tools are provided to program offices and program engineers to apply to get actionable engineering data for those programs. We provide kind of red carpet tech support while those are being executed, and we get feedback from them as well, both in terms of our responsiveness to important workflows, V&V, and then operational use. From both BAA and STAR projects, we are growing experts within our targeted communities in the use of the tools, so that our ability to provide tech support can scale over time. The local experts in the stakeholder communities, those will be their go-to people for those organizations, and when questions stump those stars, then they come to our QA groups, and we deal with them that way. I'm just going to step through the next three charts pretty quickly. Our tool that we call DaVinci is a conceptual design tool, aeronautical system design. It's model-centric. We have two talks in that blue box on the bottom left in session APA 10 later this week that detail DaVinci, and I encourage you to have a look at that. But an engineer sitting in front of DaVinci in hours or half a day from libraries of pre-engineered parts can put together a parametric associative model of an aircraft, transports, fighters, wide variety of aircraft types. So that's important to us. We can scale the ladder of fidelity of analytics from lo-fi that almost don't require even geometry all the way to the highest fidelity prediction tools. And all of the geometry attributes are derivable directly from a common DaVinci-generated parametric model. Helios is a high-fidelity, multidisciplinary physics-based simulation software product that targets rotary wing aircraft concepts. So this is a complete aircraft, arbitrary shaft angles, arbitrary rotor configurations, any concept that you can come up with. There are three shown here, but anything you could really imagine, quad rotor, tilt rotor, compound helicopter, small UAV through heavy lift concepts. High fidelity analysis can be attacked through Helios. Kestrel, which Dr. Morton will talk about shortly, is the fixed wing counterpart to Helios. It couples in a high fidelity way aerodynamics, structural dynamics, propulsion, and flight controls. The blue box on the bottom right points to several sessions here at SciTech this week where you can get detailed information from developers, from applications engineers, from DoD as well as industry. And then finally, you'll get a lot better taste of Kestrel from Scott right after me. Then Dr. Smith will share Lockheed's experience with Kestrel, and Dr. Narducci, Boeing's experience with Helios and Kestrel. And so I'll turn it over to Scott and cede the 56 seconds remaining to me to you.
Thank you. I'm going to move over the podium because I like to point at my slides. and I'd rather not laser beam General Nielsen. We call that career shortening in my life. So yeah, I'm the principal developer for Kestrel, and I'm the team leader, but I'm also the software development manager making decisions on what will be in the next versions. I'll skip over this overview, but Kestrel is high fidelity, multidisciplinary solver. It uses a multi-mesh paradigm, so we have unstructured in the near body and Cartesian high order in the off body, and that's automatically, the off body is automatically developed for you. It's high order Cartesian, as I said, adaptive mesh refinement, so you can really track vortices and shear layers and things like that away from the vehicle. And it's fast overset connectivity. It's a hands-off. There's no hole cutting parameters you need to put in or anything. It's all developed from the mesh system automatically. So, and then we handle any issues with connectivity on the fly. It's a full spectrum of aircraft types. We can do tankers and fighters, and tankers and fighters in combination, from UAVs up to supersonic fighters, and a full spectrum of flight conditions. Really very low speed, transonic and supersonic. At the inception of Kestrel, we opted out of hypersonics at the time due to manpower and funding limits, but we are now in a hypersonic push. So that's going to be going on over the next decade, is a full production level hypersonic solver available to the community. And really, we're after the operational conditions. So when an F-18E lands on a carrier deck, we have Dr. Green and Brad Green sitting here. He's actually running those calculations now, where he lands an F-18 with control surfaces on the deck of a carrier. That sort of thing is kind of calculations that are happening right now. We're also interested in KC-46s refueling vehicles, and all this can be rolled up in a very, very quick manner. One of the things to note here, sorry, I did the same thing everybody else did. 391 licenses are out there today. That's as of September. So I can remember in the first day we talked about Kestrel and we started trying to lay out how many people we thought might want to use the code. I remember we had 185 targets, something like that. And so I'm very pleased to see that we have active users, 391 licenses. Those are this year. So that's pretty exciting. And they're in 21 defense organizations. All major manufacturers are actively looking at Kestrel right now. We have affiliated organizations from NASA, Department of Energy, things like that. And then we're starting a push into academia. Of course, it's an ITAR code, so we have to do that in a special way. But the all the service academies plus 4 academic institutions are looking at Kestrel today. I don't want to spend a lot of time on this, but I want to say that it's a very modular code. And if you look at the bottom corner here, these are what you would call our delivered software to the general user components. It's very modular. It's easy for us to add new capability over the years. It's very isolated for that particular thing you're working on. And it lends itself very well to development over the years. We are also looking into, here's the hypersonic push with new chemistry and closure equations, things like that. We also are looking into high order unstructured solver in the near body, and that'll be presented by Ryan Glaspie here at this conference. You can go look at that. But one of the more unique things about Kestrel is we also allow for plug-in architecture, which means that a using organization that has their own solver or their own, more likely their own autopilot or their own post-processing tools, they can plug that in from our from our executable code with their own shared objects. And we have instruction manuals and example problems and everything. So this is critical because when you have a company like Boeing or Lockheed or Northrop Grumman, Raytheon, these companies are betting their company on the tools they use, and so they need to be able to bring in their own things, but still take advantage of this system-level approach that this tool offers. So we really needed to make that available. We also have a user interface that's very intuitive, and this plug-in architecture is automatically fully part of the user interface and the post-processing and everything. As far as software discipline, we run over 20,000 regression tests every night, different compilers, many different cases, 18,000 of them actually. And then every 2 weeks, we're on a Scrum type development process where we read V&V the code every 2 weeks. So we always know where we're at with, and that's about 132 different full aircraft kind of calculations that we do. It takes about 4 days to do it. So it's a pretty well-disciplined aircraft analysis tool. Now this is what I wanted to really get to is the most difficult problems that we're seeing in acquisition are really multidisciplinary. So it's not the the aerodynamics, or it's not the structures, it's the combination of those two. It's not the aerodynamics or it's the flight dynamics, it's the combination of those two that are the issue. And so we really wanted to bring a new tool to the toolbox of the government and OEMs that would allow them to look at the multidisciplinary problem easily and effectively. And so that's what we went after with Kestrel. The majority of tools out there in the government and in the OEMs is really single disciplinary. It's difficult to find any multidisciplinary tools out there that are at a production level. And so we really went after that. It's critical to early detection of the costly defects. And we really want to move this detection early into the design process instead of waiting till a airplane's flying to detect that. And so we designed it from the ground up to go after these multidisciplinary issues and help the DT&E engineers run these codes. So here's an example of a multidisciplinary case that we designed in Kestrel from the ground up. This is an example of the F-16 limit cycle oscillation that's routinely seen out at Eglin Air Force Base. And so we've developed the capability where you can attach a store which has its own mesh system and an aircraft with its own mesh system. And you saw it actually, that was a release, like an emergency situation where you pop the store off. And so, and we can even, that has impacted the structural dynamics by dropping that store off of there. And to the user, you just build your grid system for the F-16, for the store, your mass properties, your structural models, independently, tell them where they go together, and we handle all the details of tracking how those things move in time very easily. So what are we able to do? Limit cycle oscillation analysis, multi-body aeroelasticity, maneuvering with aeroelasticity. So this thing could be in a 2G wind-up turn when it's doing this, just as easily for Kestrel. The next multidisciplinary case is propulsion integration. And really almost all DoD aircraft programs have issues with the installation of the engine. And again, you don't see it until very late in the process. And so here's a situation, it's one of the first calculations I've ever seen. At the time, it is an A-10, full aircraft A-10 model with a rotating machinery on the inside of there. And on the left-hand, or the right-hand engine for the pilot, it's a fully rotating machinery, and on the left-hand side, it's an engineering model, the cycle deck. So we're able to run in Kestrel both the cycle deck and the rotating machinery and see how well that model does for you. But if you can see, this is at a particular angle of attack where it does a lot of unsteady ingestion into that fan and can cause unsteady vibrations of those blades. So this is where we can start to attack the inlet integration problem before it's even an airplane, when it's still an idea. The next one I want to show is the store separation analysis. So this thing will cycle a few times, but take a look at that store when it leaves. You'll see how close it gets to the fuel tank right here. That's within 2 inches. And that actually matches data very well. But the idea here is we want to be able to do these kind of store separation calculations before the airplane gets onto the ramp. And there's too many download cases to do that all with flight tests. We just don't have the runways, the airplanes, and the time to do it. So we need to go to a modeling approach to handle this. And Kestrel can do both the matrix approach, where you sort of build up a model with these things at different stations and do it very fast offhand, or you can do the full trajectory analysis and look at how that would happen. And this is an actual case that we've looked at. Here's another one where it's very critical that a flight control system begin to be integrated earlier in the process as well. This is a case where we have a UH-60 helicopter, and there's a Castle is a fully integrated flight software from NavAir that has the flight control laws and the pilot model. It has landing gear model so that when it drops down, it bounces on the tires. And so what you're looking at here is this helicopter is now descending behind its hangar on the deck of that missile frigate. And you can see how as the airflow influence from the ship begins to shred through that rotor, and it really changes the aerodynamics on the helicopter and on the deck of the ship where people actually have to stand. And so people at Brad Green's shop, Susan Polsky's group, they're really interested in doing a nice job with this. But until you can couple the helicopter and the ship and the flight control system, you're not going to be able to do these things effectively. And so this is an example of a plug-in of the flight control system for that helicopter, Castle, is sitting on the outside of Kestrel, and it's only executable code given to the group that needs to do this calculation. So really this coupled flight control system with the aerodynamics, with the structural dynamics, all of that is critical to being able to do these multidisciplinary problems. And it's pretty straightforward to do with Kestrel. Now, I want to make the case that those are really cool simulations by themselves, but every one of them is a point design. Every one of them is a point in the sky problem to go look at. And really, conceptual designers, flight control engineers, structural engineers, they have very little use for a single point calculation. And that's why it's been so hard to push this into flight control's realm and in the structural realm to do these high fidelity simulations, because they need a whole envelope worth of calculations to be effectively using these tools in their design process. And so we need to be able to take, a high fidelity multi-day simulation, 4-day simulation, and somehow make that usable to these flight control structures, propulsion engineers, on a laptop, so they can run these calculations over and over. Conceptual designers, they really need a whole aircraft envelope aerodynamic database to do their performance evaluation. Flight controls engineers need, microsecond response times on the aerodynamic database so that they can have their controllers calling that data up. And then structural engineers, they need distributed loads that run on a workstation so that they can do the structural analysis for the whole vehicle. And we need a method of taking these simulations that take days and then given this very fast offline reduced order model kind of approach. So I want to show you how we do it in Kestrel and make the case that this is how we should be going in the future, is being able to take these high fidelity simulations and go to a reduced order kind of approach. So here is the Kestrel model building process. So in Kestrel, you're able to take your mesh system and do your aerodynamic calculation and do a prescribed motion. In this case, it's just a sinusoidal, multi-frequency, multi-amplitude kind of motion. And then you know the inputs and you know the outputs, and you can develop a system identification model. And from that model, you can either do a dynamic maneuver by just replaying, plug in alpha of time, beta of time, PQR of time, and get your lift drag moment terms out of it. And here's an example. This is actually an actual calculation of, and it has a CL alpha curve, so we zeroed all the dynamics terms and checked the static points along the way, and you can see we nailed it really nicely. So this is a way to develop a model in a regressor space. So you go out and you really go after all the alpha, beta, PQR kind of combinations in a maneuver, and then as long as your flight test maneuver or is within that regressor space, you should get a good response out of that. And so this is the process in Kestrel, but I want to show you it applied to an F-16XL, very complicated aerodynamics problem that has many, many vortices interacting. It's very nonlinear, and I want to show you how well that did for this process. And I only went through the process one time. So what you would do is you would go through this process once, and if this didn't show you a nice behavior on this curve to the right, you would say, I need to increase my maneuver to go after more regressors and turn the crank one more time. I'm going to just show you one pass through. So this is the F-16XL. The F-16XL was in competition with the F-15E, but it became a very nice NASA DoD experimental tool after the F-15E won that competition. But it's a delta wing F-16XL, much expanded wing. And what you have is you have leading edge vortices, strake vortices, leading edge surface vortices, outer panel surface vortices. You have AIM-9P vortices, and all of them are interacting on this outer panel to make a very, very unsteady flow. And so what we have done is created a sort of optimized maneuver for the ranges of interest, alphas between 10 and 20, betas between plus or minus 6, and PQR rates between plus and minus 35. So we built this maneuver using Hal Carlson's toolbox, and you can hear a little more about that at Aviation Conference this year in June. But this is the alpha beta trace, and these are the PQR traces. And it just goes through this maneuver. It's not the maneuver a pilot would fly, it's a maneuver that's computationally best for us. And once you do that, you now know the inputs alpha, beta, PQR, and you know the outputs lift, drag, and moments. Lift, drag, pitching moment, side force, rolling moment, yawing moment. You know all that data as a function of time for that maneuver. And so now you can build a system identification model of that. I'm showing you lift, drag, and pitch. But these are a lot of terms. They're very nonlinear. They contain all that nonlinear data that we gathered in the CFD high fidelity process. And probably about 38 terms or so there. And it's, you can choose how many of these basis functions you allow, how many, the order, third order in this case, and then how many multiples of variables you allow. But when you're done, you've got these models that can either be run with another maneuver, so now you specify alpha, beta, PQR as a function of time, or you even just say, I want alpha and beta of this with no PQR and get some static data out of it. And so here's an example of lift, drag, and moment, and I want to show you how well the model did. And so this is lift, and then a sort of a focus in on lift, drag, pitching moment, and focusing in on that. I want to point out a few things that relates to the F-16XL. First thing to notice is the black is the CFD and the red is the model. The model goes right through the data for this training maneuver. So we were very successful in modeling that particular training maneuver by the equations that we came up with. The other thing that I did was the F-16XL has vortex breakdown. It has all this unsteady rotating vortices, and the loads are changing in time. That is cannot be a function of alpha, beta, PQR by itself. They develop in time. So what happens is when I do a model of that with alpha, beta, PQR as my terms, I throw away a lot of information about the unsteadiness of that calculation in the CFD. So what I've done here is I've built a model of the min and max around that, so what I call unsteady bounds. So now I not only know what the behavior is of the mean of the vehicle, I also know how much it's oscillating between them. And so this gives us another level of information that we don't have. And you could even model, if you're doing like a man-in-the-loop flight simulator, you could even pick off the dominant frequency and build your little sinusoidal in there and say, it's going to behave something like this with these bounds. And the pilot starts to get a sense of what that unsteadiness would feel like. Or you could apply that to a fatigue analysis in structures, things like that. So here's an example of the off-design prediction maneuver. I just built a 10 to 17, minus 4 to 4, and plus or minus 5 PQR maneuver just to see if I do something within the regressor space, can I repeat that with the model? This is not the training maneuver. This is a full prediction with the model compared to a CFD of this. And so here's what we get. Again, data flies right through the model, flies right through the CFD unsteady answer. And even better than that, my unsteady bounds are predicting the level of unsteadiness at places that were not in the training maneuver. You know what I mean? Not specifically a point in the training maneuver, they were the modeled unsteadiness. So now I can really look at the unsteadiness that comes from that. So this is pretty exciting. This is something that now, on a laptop, we can use that CFD high fidelity data, but use it in a design sense for the community. The next thing we did was take a look at how well would it do the static data. So I did a very dynamic training maneuver, and I'm now looking at the static components only. So this is outside of the training maneuver, regressor space. And so we took a look at a comparison with 10, 12.5, 15, 17.5, and 20. And this is what the flow field looks like. So it's a very complex flow field. And so this is what we ended up with. And so this is where I was talking about you would do one more pass with this. I wanted to show you when it didn't act perfectly. So in this case, we were able to match the CL alpha curve very well. The dots are the static data, and I'm predicting the bounds of it, and I'm predicting the behavior of the thing for lift, side force, rolling moment, and yawing moment is predicted very, very well. The drag is off in this delta here, and that's because I didn't dwell long enough in the maneuver. So when you saw this, you could go back in and you could add some slower dynamics to capture this behavior and then build your model again and capture it. We've done this in the past, and that's exactly what's going on here, and we've been able to fix that behavior. So even though I'm showing you not a great fit here, you're still getting an excellent trend, and I'm also getting an excellent bounds prediction on the unsteadiness of that static data. And so this, I'm confident, will be fixed in a second pass because we've done it with many other vehicles already. So, summary, Kestrel has proven to be an accurate, robust, and efficient tool that's easy to use. You'll probably hear a little bit about that from the industry folks. It has been, people have commented about how easy it is to get up and running and get started and do a very complex problem with Kestrel for the DoD, the industry, and academia. The importance of system-level analysis, I hope I've conveyed that to you, that that's where we need to be going in the future, and the importance of model building so that we can hand these solutions off to the designers, the flight control developers, the structural analysis people, so that we can find these defaults very much sooner in the process. And with these advanced capabilities, I think we can shift the paradigm that Bob Meakin talked about and go to a design, simulate, fix, test paradigm. Thanks.
Good morning. I appreciate the opportunity to talk to you this morning a little bit about CREATE and the Lockheed Martin experience with the tool and how we've been working with the CREATE AV program. And I'm going to talk a little bit about kind of some sort of philosophy and how we see the importance of this kind of a program, and then I'm going to show some examples of some of the validation and demonstration work that we've done with CREATE AV tools, working with the CREATE program. So, obviously I think everyone in the room understands there's a huge payoff in reduced design cycle time and cost through increased use of multidisciplinary analysis and model-based design tools. And at Lockheed Martin, we're moving aggressively to increase our capabilities. An example of that, we have a 4x increase in our computing cores in the last 3 years, just due to the demand of our programs and the capability that we gain from using this kind of capability. But the problem that we've seen historically is that there just isn't the investment in software that there is in the hardware. It's so easy to just roll in hardware, spend a few $1 million, and it's like crack. You get instant capability that you didn't have before. But the software there's a huge payoff and need to invest in the software to really take proper advantage of that hardware. There are a couple aspects of that. And the first thing is, some of the software that people on this panel have developed, like say the overflow code, it's around for 20, 30 years. People are still using it. You're still getting the benefit of that investment. It takes time, but there's benefit. A supercomputer in 3 years, you're going to have to replace it. It's gone. It's almost worthless. 3, 4 years, you're off for a new one. And then just to make the capability really work, obviously to get the accuracy that you need and is a key part of it. And in order to get that accuracy, we need physics-based models that for turbulence, combustion, transition, fatigue, structural damping. There's a big, and that's, obviously there's a big list of the kinds of things that you need. Finally, investment in software means that you could make sure that you can efficiently use the hardware. It's easy to have an inefficient piece of software and chew up lots of CPU time, where a relatively small investment in the software will make you get better use of that hardware. So from our perspective, from my perspective, it's great to see the government investing in the CREATE program, that it's more, the HPC is more than just getting more hardware. If you build the hardware, we'll just fix all these problems. This is the kind of investment that we need to really leverage the capability and get where we need to go. The other point is that, we need to work to validate the tools. And there's, I think I skipped one here. So, the second part is that, there's a paradigm. I'm going to go over this one pretty quickly, but, for both industry and customers change, a paradigm shift. Customers, everybody likes to see hardware. They love to see hardware in the tunnel. They like to see something happening as quickly as possible. And that's not really consistent with what we really want to be doing, which is doing a model-based design and doing an awful lot of work up front with our designs, and then go to the wind tunnel when the configuration is more mature. And so, that paradigm shift is something we have to be aware of, that in industry, we're responsive to our customers, and our customers want to see something that keeps their program sold. And obviously, we want to get to prototypes as quickly as possible, and a model-based design helps us to get there, but we want to be doing meaningful tests and not doing tests that just show that, oh, we're doing something. So that's something that, from a whole industry customer standpoint, there's some work to be done. Finally, obviously, in order to use these tools, we need to validate it. And I think that in industry, we're really the guys who have to sign up to getting something done and then make sure it flies. So we're the ones who have to we have to be convinced that the tool works, that the results are reliable, and that we can trust it. And so we have, I think, a really good role that we can play in working with CREATE programs and other efforts to make sure that the software is providing the capability that we need to do our job. And that's an important part of moving to where we really want to be. So just kind of bottom line here, we think the CREATE toolset enables a collaborative, multidisciplinary environment for both government and industry to work together. Okay, so this case, it's a transonic case. It's not a simple, cruise condition. This is looked at F-35, 14-degree angle of attack, a leading edge flap deflection of 20 degrees. So it's a pretty complicated case, and we compared the two codes for this. So what you see here, these are the contours of the pressure coefficient. On top are the results with Kestrel, with the Spallard-Almaris RC model, one of the models that are in there. On the bottom, you see the Falcon, our Falcon code with the algebraic stress model. So kind of just to sum up, we found the tools highly capable with potential for expanding multidisciplinary analysis. So we can help shape the CREATE development in useful ways. We have realistic problems. We have real test data from wind tunnels and flight tests that really are a great test bed for all this capability. We have stringent accuracy requirements. We have demands to make sure it actually works. And so I think that we are, in that way, we're a very useful partner for the CREATE program. And then, of course, also, we've got the design environment where we're really trying to turn things quickly. Again, we're able to really provide a good platform to test the program. So, we can just want to say I think it's been a good collaboration, and the need is there to continue to work the software in order to make high-performance computing really pay off for the aerospace industry.
Good morning, everyone, and thank you for the opportunity to share some perspectives from Boeing on the CREATE tools. And I'm going to do that by first giving an overview of the philosophy of CFD at the Boeing company. The direction that we've gotten from our CTO for many, many years has always been to have a set of tools in our CFD toolbox that is compact, in the sense that we don't have very many tools, but just a few tools that are very flexible, that satisfies a lot of the needs for the many diverse products that the Boeing company offers. And this has a lot of advantages, and one of those advantages is really low maintenance costs. There's a lot of commonality across the corporation from the East Coast to the West Coast. Training costs are low. When you make a modification to one code, you don't have to do it to 100 codes, you just have just a few. This enables a very uniform, high-quality set of CFD solutions that come from the Boeing company. So whether it comes from Philadelphia or whether it comes from Huntington Beach or St. Louis, our customers know that the CFD solution that a Boeing company produces is got some good quality to it. With just a few CFD tools, we also have very well-established processes. They're well-validated, well-documented, and because of that, having such longevity of certain CFD tools, it's very difficult to replace it with a different CFD tool that does something that is just maybe marginally better. So with that, Boeing's not really looking for another CFD solver that can do what we already do well. So while we're not static in our CFD tools and processes, we're continually to develop. We develop the same stuff, and we put new stuff in our same tools. Incremental improvements isn't going to cut it for introducing a new code, because that would mean that we'd have to revalidate over a number of configurations and operating conditions. So instead, we invest in new processes built around the same tools. Enter CREATE AV. Now, this is a slightly different scenario because the DoD has developed these tools specifically for the acquisition of new products. And so now you have our attention. All proposed vehicles from the Boeing company are going to be analyzed with Kestrel or Helios. And it is beneficial to us, before they start to evaluate our products, to know what Kestrel and Helios are going to say about our products. Ideally, they give very similar answers, and we'll be on the same page with how the vehicles perform. That may not always be the case, and so we want to know if that's not the case, if we are going to get different answers between our legacy tools and what Kestrel and Helios are saying, then we want to know that ahead of time and be able to come up with arguments why we think one is right, or if we think that Kestrel and Helios are right, well then that gives us some impetus to understand why our tools aren't behaving the way that they should. In the case of Helios, now we still have some of the challenges with bringing in a new tool into the Boeing company, because now we have to do certain validation all over again, as Dr. Smith had mentioned. We're on the hook for understanding what the tools are bringing, and we want to make sure that the tools are going to be accurate. In the case of Helios, Helios is a multidisciplinary CFD tool. So inherent in it is a lot of different CFD solvers, and one of them happens to be Overflow, another one is Fun3D. Those are tools that we already have at the Boeing company, so we understand what those tools are going to bring as far as answers and the accuracy of those tools. And so there was a lot of, there's a lot of benefit in bringing in Helios because we already know what the solver is going to do. Kestrel is a little bit of a different animal here because it had the KCFD solver, which we were not familiar with before we brought in Kestrel. However, there were a lot of advantages with Kestrel that were worthy of taking a look at Kestrel. For example, bringing in things like the store separation, the maneuver flights, the integration of the propulsion system. So all of those things made it attractive, and that's why Kestrel is starting to infiltrate some of our fixed-wing programs. There are other elements of the CREATE AV tools which are also attractive. First of all, CREATE AV is financially backed very, very well. And because of that, that means that, the capabilities that Kestrel and Helios have are well verified. That means that when we get it, we know that they're going to work. They're well validated on their end. There's tutorials, there's documentation. All of that stuff is done very, very well for us. Also, as Dr. Smith had mentioned, they're easy to use. We went through an exercise several years ago where we took several CFD practitioners at Boeing. Some were brand new CFD people, some were 5 or 6 years of CFD experience, and some were more seasoned. And we took them all through the Helios and Kestrel training. And then we told them to work on something else for a month, take a hike for a month. And then we brought them back, and we asked them to do a problem in those tools, and they had a very easy time in being able to pick up where they left off. There wasn't a lot of thumbing through documentation. Everything seemed like it was straightforward, and it made a lot of sense as far as the workflow goes. So all those things have benefits to bringing in these tools. And finally, the last one is a licensing issue, and that is once you have the user agreement in place, you can run as many simulations at the same time over any number of compute nodes without having to worry about a license availability issue with Helios or Kestrels. Again, as I mentioned, some of the challenges that I mentioned earlier still persist, and while in the DoD there's a lot of motivation to look at Kestrel and Helios because that's what our products are going to be evaluated from the DoD. From the commercial side, there's a little less motivation, although they are keeping a keen eye on the CREATE AV progress, particularly when it comes to aeroelastic capability. But as far as the penetration of the Boeing company, it's more on the DoD side and less on the commercial side. As I mentioned, and Dr. Meekin had mentioned, there was a few BAAs that came out a couple years ago, and some of our experiences have been documented in AIAA papers, and so these papers are listed here. Now, some of the papers, some of the older ones from the 2015, there was a lot of, not a lot, but there were some issues that were brought to the attention of the developers, and those have been taken care of. So as you read through them, some of those issues have been resolved, which has been a terrific thing, and that's another result of having a well-financed program, but also having engineers be the developers and have them understand what we're talking about when we come back with feedback, and then them being willing to respond to that. The last paper there is one that looks at an Apache in hover and forward flight, and this was, because I have a rotorcraft background, this is one that was a lot of fun to work on, and this particular problem looked at an aeroelastic problem with the blades being flexible, and we used an overflow and a structured overset mesh for the blades because that is a very efficient way of generating a grid for a blade, and it's efficient to make, it's efficient to compute on, and it couples very well with a comprehensive code. The comprehensive code provided the aeroelastic deformations and the control systems, control settings, so that we got a trimmed solution. A rotorcraft solution has little benefit unless it's trimmed. In other words, you don't want to have a rolling moment unless it's intended on the rotor system. The Apache fuselage is more like a machine gun than a helicopter, and it's got a lot of detail, and it's very, very difficult to grid if you're trying to do it with a structured approach. Helios allows you to use an unstructured approach, so the fuselage was very, very quick to grid with our structured grid generators. And then because we have a lot of the interactions of the vortices that interact with themselves, they interact with the rotor blades, they interact with the fuselage, it was important to capture those very, very finely, with a lot of detail, and because of that we had an adaptive approach which is Cartesian. So the Helios framework, you could really tell it was designed by helicopter engineers that had a unique capability of not only understanding the helicopter problem, but understanding how to program all that into a system that could easily do the problem. This is a picture of that solution, but I just wanted to conclude with just a few thoughts, and that Kestrel and Helios are really advancing the CFD-based multidisciplinary problem. A lot of the solutions that we do on a routine basis at BDS, at the Boeing Defense Systems, have been, some of them are routine, but now as we start to go to the multidisciplinary analysis type, Helios and Kestrel are really positioning us to be able to do that well and to do it accurately and to do it efficiently. So the addition of the CREATE AV has really been a blessing into the CFD toolbox at Boeing. I think it does provide us it keeps us competitive, and ultimately what it does is it improves the DoD assets, which is very important for this country. So with that, I'll turn it over to Dr. Kraft.
Thank you. Well, good morning. I'm the cleanup hitter, and it's my job to pull this all back together and try to emphasize what is different about having CREATE available to the aerospace and defense community. And And its title here, as Paul pointed out, I've had an extremely long career in the aerospace and defense industry, and this title encompasses what I consider two of the major highlights that I've had the good fortune to have a front row seat. First was the formulation of the CREATE toolset and CREATE AV in particular. It's not happenstance that the features of CREATE are as robust and impressive as they are. Bob and Scott, day one, they took apart 27 engineering applications of physics-based modeling across the entire life cycle of a system to define the initial requirements for CREATE. That's all the way from conceptual design, detailed design, testing, maintenance, manufacturing, all the way through. And they very systematically looked at what are the features you would like to have in order to work across that entire environment, including things like airworthiness certification, weapons, air armament, carriage and release certification. And they systematically evolved the kind of tool set you saw, so it's not accidental. The other part of that equation is 4 years ago, the Secretary of the Air Force and the Chief of Staff of the Air Force directed the Chief Engineer of the Air Force to put together an engineering enterprise strategic plan. And that's been implemented, and we're working on it collectively across all the senior leadership, engineering senior leadership in the Air Force, and it's evolved into a concept called digital thread, digital twin. And now I'm going to show you the convergence of why CREATE is such a major enabler for that broader vision the Air Force has on how we transform engineering across the entire life cycle of systems. You'll hear me talk later on a value function for what we do with aircraft in the Air Force. And to me, it's a real simple value function. If you define value is a utility function divided by cost. I think the value function for the aerospace industry, aircraft industry in general, is how many aircraft are available on a ramp today, and what was the total ownership cost to have that aircraft available. As you'll see when we start taking a systems look of all those places where you can impact that value, you'll see where the footprints of CREATE are a game changer in what we're talking about. So that's what I'll try to do in the next couple of minutes if I can figure this out. The big green button, that's pretty good. If you're not aware of it, there is a pretty significant digital engineering revolution going across the aerospace and industry, or aerospace and defense industry. It actually was led by industry. You know, they, a number of years ago, start building digital engineering approaches to their process, going from 3D CAD drawings through their manufacturing processes, their logistics processes, their assembly processes, and so forth. And what the government, particularly Air Force, has been looking at, okay, what about all the things that go on before design? What about all the things that go all the way back to requirements definitions and analysis of alternatives, and all the things that go all the way to the end of life for a system. So the Air Force has been moving towards an Air Force digital thread, digital twin, which encompasses that entire environment and is intended to be a collaborative environment of industry and the Department of Defense working together. And you're starting to see the technical societies, including AIAA, I think they've got a session Wednesday night to start pulling together, you know, the future directions AIAA wants to work in and propagating digital engineering across the industry. As you'll work through this, the whole concept of digital engineering really is an integration of model-based systems engineering and model-based engineering to affect a different outcome in a life cycle of systems. CREATE, particularly CREATE AV for fixed-wing aircraft that we're working on, is a key enabler to that. And I think you'll see those attributes as we go along here. Put this at the Department of Defense level. This isn't just the Air Force, the entire Department of Defense is moving in this direction in concert with industry. This is a very positive step, I think, in a collaborative environment we have to have. Now, the key things here at the Deputy Assistant Secretary of Defense Systems Engineering Shop at the OSD level, they're the ones who write policies for these kinds of things. And if you get online and look at defense acquisition guidance, you'll see the shift to digital engineering. They're moving away from terminology like modeling simulation to digital engineering being the all-encompassing processes, tools, and et cetera to deliver a different output. They have specific initiatives going on. There's a defense engineering working group looking at how do you create a digital ecosystem to enact these kinds of things. They're investing in capabilities like engineering resilient systems, which provides a lot of the structural tool sets to support a lot of decision making across the Air Force. And then you start coming down through that middle column there, and you see at the bottom is CREATE is already identified as a key enabler at the DoD level. And this is CREATE in general. This would include ships, ground vehicles, future things like hypersonics in space. So at the DoD level, it's recognized where the role of CREATE fits in this. And now they're starting to work with industry and the services to let's go actually put rubber on the road and implement these ideas. And so you see towards the bottom of the right-hand side there, the Air Force is working on a digital thread, digital twin, own the tech baseline, broad initiatives across the Air Force under this engineering strategic plan to affect a different outcome. So that's kind of what we're going to start highlighting. If you go online and go to the Defense Acquisition Guidance, you'll see some of the formal definitions for digital engineering. It's basically transferring paper to digits. Now, I want to be very clear up front. This is not just take our conventional processes that we've been doing for years and building digital forms that you can fill in. Now, this is transforming how we do business because we can use digital information in an integrated fashion over the entire life cycle. And we can share knowledge in ways we've never done before if we get the knowledge converted into the right formats. So that's the concept we're talking about. So I won't belabor these definitions, but that's the broad view, that we're in that paradigm shift, going from paper to digits. This is the Air Force's analytic framework. This is affectionately referred to in the Air Force as the birthday cake chart for obvious reasons. But it encapsulates what we're talking about. The end game for engineering analysis is at the top of the chart. It's to support decision making. And you want to bring quantified information in terms of probability of cost, probability of performance, probability of schedule to a decision maker so he can look at scenarios and make considered judgments. And that's at the highest level of the Department of Defense, comes on down to the Air Force acquisition, down to the PEO, program manager. Now, it's nice to have all the neat CFD solutions and graphics that go with that, but that's not what decision makers need. They need quantified margins and uncertainties about performance. So if you go to the bottom of the chart, it starts with having a digital collection of knowledge and data across the entire life cycle. We have multiple stovepipes today, and we're having to learn to integrate those. We have people who do developmental planning. We have people that do technology development. We have people that do detailed design, mainly the OEMs. And how do we translate OEM designs into digital information for life cycle? We have test information. We have supply information, maintenance information, operational information. How do we transform all that data into decision quality information at every part of the life cycle? And so I go from the bottom of that chart, the so-called, basically the knowledge base of technical data, and I transform that into decision-making information. Well, the first step is direct application of tools like CREATE AV in particular for aircraft. I take dimensional drawings, I take outer mold lines, and I start analyzing the performance of the system and comparing those through model-based systems engineering with requirements. Am I getting the range? Am I getting the climb rates? Am I getting the turn radius? Am I getting all those key performance parameters satisfied? And can I do that early as an integrated system? That is the first part where the engineers really do the heavy lifting. And that's useful information to the program manager, but he still needs the next level. And as you saw Scott point out, the ability to go from those very high fidelity physics-based modeling into reduced order response services, not reduced accuracy, reduced order response services, allows us to do probabilistic analysis of cost, performance, and functional utility. That's where you start translating information into information for decision makers. So you start moving up that vertical chart. That blue line crossing that is called digital thread, digital twin, and I'll make that a little more obvious too as we go along. How do I capture and use knowledge over the entire life system, moving from concept all the way through sustainment and moving from sustainment all the way back to concept? That's what the digital thread is all about, having digital knowledge. Everyone in the system has access to the same authoritative digital representation of the system. I'll illustrate a little bit later on, but for example, at the far left, I'm doing developmental planning, and we create concept vehicles, and then you all go down to a solution. We can apply Kestrel and get you a flyout model, and also a load spectrum model. I can project that model It's a paper airplane, far left. I can project that all the way out to surface life extension. I can use that load spectrum to tell you what your optimum surface life extension program would look like. Flip side of that is I'm capturing operational and maintenance data by tail number, by part number. And if I apply big data analytics, I should be able to tell you the effect of design variables all the way to the left on sustainability all the way to the right. That's the concept of the digital thread. I carry knowledge across the entire life cycle. So that's some of the tenets of the digital thread, digital twin, and disappeared on me. Let's see. There we go. One is everybody in the pipeline has to have access to the single source of authoritative representation of the system. This entails then an obvious, very close collaboration between industry and the government. And we can't have multiple versions of this and multiple versions of that. There has to be a single authoritative digital surrogate. And everybody's on the same page together. As Dr. Arnauducci pointed out, if they're going to have the government evaluate their system, they definitely want to have tools like CREATE model that system, and so we have a compatible and agreed upon definition of what the system's doing. End-to-end system model, I just described it. I can go from concept planning through sustainment, and sustainment back to concept planning. That single authoritative digital representation. Everybody in the pipeline, if a trainer needs a fly-out model for his training simulator, it's the same one the guys that are supporting operations that are doing, the same ones that are doing wind tunnel tests that are using. So everybody has the same single authoritative source. The getting to reduced order response services is done on probabilistic analysis of key parameters, affordability, et cetera, very important to this. And the other thing about having a digital environment is I can preserve all the metadata. We're facing issues with things like A10s or something like that, and you'd like to know, why did they decide to use that material in that part of the design? What if we captured that metadata and preserved that over life cycle? So when we redesign something 20 years out, we know what the legacy of that design concept was. So those are the principles we're working on in digital thread, digital twin. This starts to show how this plays and where CREATE really is such a huge enabler in this. Again, the top of that is I want to support the decision-making process. Right below that, you see what I call systems engineering leverage points. These are the places where we make or break a system value. Far to the left, if we have volatile requirements and are constantly changing on us, and there are requirements that drive us to the Pareto frontier for design, which is highest risk, highest cost solution you can come up with. That's where tools like DaVinci come in. If I can look at the complete design space for concepts and go to reduced order response services and translate those into war game engagement models so I can track mission threads and also track those into cost estimate relationships, I now have the highest probability of success of mission thread, feasibility, and affordability of a system. So I've got a much better set of requirements going into the problem. Once I get that information, I can down select to a specific configuration of interest. And if you give Scott the outer mold line for a configuration of interest, he's going to give you the flyout characteristics, and he's also going to give you a load spectrum. So I can take that load spectrum and I can start feeding that downstream, again, to the sustainment process. Now, in the lower right-hand corner, you see an additional tool set that gets into the digital twin part of what the Air Force talks about, and that's the Integrated Computational Materials Engineering toolbox. That's where you can start modeling manufacturing processes. You start talking about sustainment processes and those type of things. So by tail number, by part number, the Air Force intends to monitor stresses on the aircraft and use that information to reduce cost of maintenance and extend life of aircraft. All those other engineering pieces in between, these are flags. If we go into technology readiness level pre-milestone B, the big difference between the TRL-4 and the TRL-6, and it's of the order of 30–40% overrun if you don't know the difference. Can we quantify that difference? And as Scott pointed out, one of the advantages of the CREATE AV tool set is I can design an integrated system. In my 100-year experience in this industry, almost always the mischief in system development is the interface between subsystems. We can design the perfect aerodynamic performance vehicle. We can design the perfect I-beam. We can design the perfect isolated engine. It's when you put them together that you have all the discovery problems. CREATE now enables us to do the design. The integration is a design problem, not a discovery problem. If you go to the middle of that, if you get the critical design review and you don't have a closed design and you haven't completed critical drawings, you get much below about 70% of critical drawings released at CDR, you're at the 30 or 40% overrun. And I've just thrown away a bunch of airplanes and cost a lot. If I get into hard data, it says after first flight, our history is we on average find 10 structural defects in every aircraft we've ever developed. That should be a design problem, not a discovery problem. So again, pushing it further left. If I go into operational test, and I don't have a manufacturing representative test article because I've been late getting everything else done, I increase the probability of having difficulties in operational testing. And then the end game at the DoD level is this system suitable for giving to the warfighter? And it may operate the way you want it, but it may not be sustainable in the field. So you see that all those pieces have to tie together. And now I think you start to see the real leverage of a tool like CREATE, from the earliest concepts, detailed design, integrated design, and putting together the probabilistic response surfaces we need, and then feeding into the whole detailed design, manufacturing, sustainment process. So with that, let me go to my last chart, so I don't make Paul too nervous over here. So CREATE was designed from the beginning to do this. This wasn't happenstance. It wasn't made up on the fly. This was designed in. It is such a key enabler for what I've been talking about, this whole model-based systems engineering, integrated model-based engineering. And that means coupling your requirements dynamically with your design attributes. Multi-fidelity, multi-physics, and you've heard it several times here. I look at all the major subsystems as an integrated system. That's a huge change. Using proper orthogonal identification and system identification, getting to these reduced order response surfaces, which really support the probabilistic analysis of cost, risk, and schedule. And then the important thing, I hope you picked up on, this is one of the most high quality software development programs in this part of the business I've ever seen, in terms of best coding practices using modular architecture and configuration management. This capability is going to be around the next 30 or 40 years. This is not a one-shot deal. Let's go write some neat AIAA papers and brag about what we can do. This is no kidding, the toolbox, definitely the Air Force intends to use, and I believe the entire Department of Defense is used. And I think you're starting to understand from our industry partners, this is the aerospace and defense toolbox. So with that, I believe, Paul, I'll turn it back over to you.
Okay, as we transition to the question and answer period, we got about 25 questions. How do you see the CREATE suite of tools competing with commercially available software tools that are already out there in the industry today?
Yeah, sure, and whoever else wants to chime in. So what we're doing is developing capabilities in response to prioritized requirements of the services. And some of those requirements are really niche markets. They're really important to the Department of Defense, and for a commercial software house, it's probably not a business model for a lot of the things that we do. But at the end of the day, we're in this to help the Department of Defense be successful, and whether it's a niche market or not, if it's important to DoD, that's our charter to be responsive to that. And so that's our
Yes.
prime objective. Yeah.
Anybody else want to comment on that, or?
Yeah, I would say that we targeted multidisciplinary because that was not in the available software. We did evaluate available software to see if
You don't want
we
to
could do a
reinvent the wheel,
fluid
obviously.
structure interaction problem on a real airplane configuration, and that was lacking. And so we went after those multidisciplinary aspects, and we found that if we were as good as the CFD solvers out there, because they are good quality software products,
Yes.
then that hit the target for us because we were after the multidisciplinary side.
Yes.
So we're not trying to be in competition with them. We're trying to offer a multidisciplinary tool.
Okay, great.
for them.
Okay, here's a good one. What is the availability of CREATE software to academia? How would academia start to participate in this? Move your mic. There.
There we go. Yeah, so Doug mentioned earlier for the CREATE program in general, Access requires a contract with the Department of Defense. The air vehicles component of CREATE is a little bit unique. We have an HPCMP memo and directive that allows us to grant access to requests for, of course, the DoD direct case, but pre-program work, IRAD work that has eventual DoD applications are also acceptable. And then thinking in terms of manufacturers having a workforce training on requiring multiple tool sets, that's a bit much. It's important for the national defense interest to have a healthy and robust domestic aircraft manufacturing community. So our use case allows military and commercial applications of the tool sets subject to our abilities to support it and subject to export controls.
Yeah.
Now the academic question, universities that do defense work, many have ITAR certified labs,
Yes.
And in those we can provide access to full-featured CREATE tools. We're also actively looking at an approach to provide reduced capability tools that can be used in classroom settings and outside of those specific labs. So we're in process of coming up with such a deploy.
Now, there's another question that's lower down on the list, but that kind of relates to this, I think, and that is, how does CREATE license this work? How do people have to pay for a license? How does that work?
Yeah, another good question. The license is the license for access to the tool, and so for government uses, there's no cost associated with it. So you apply, and basically you're agreeing to not share the software with anybody, and it's subject to export control laws, which are defined in the license.
Yes.
For non-government uses, then we are required to recover our cost for technical support and testing.
Yes.
So there is a nominal fee associated with that if it's commercial use.
And do you license pieces of it at a time, or the whole access
No,
to the model?
when you're granted access, you're granted access to any CREATE AV
Okay,
tool.
great. Okay, how does CREATE interface with other sort of non-HPC models? You know, if people are doing some modeling early on with other tools that are available, how do they go back and forth between that and HPC models?
Well, sure, I'll take it. That is the vision for Da Vinci, is that we're developing Da Vinci to be able to take, very quickly get to the mesh for the aircraft or the missile or the weapon. And so the idea there is you should be able to take a low order solution with a 3-view drawing, turn that into a 3D surface that's meshable. And the vision of CREATE, which is happening over the next version or two, is to automatically generate both the near body and the off body mesh. So once you have the solid model of that vehicle, you're ready to go. Hands off, send off your flight conditions, and it builds those meshes for you. That's version 8 and 9 kind of capability for Kestrel.
Let me add a little bit to that, Paul.
Yeah, please.
If you take the vision Sky's laid out, where you can go from a paper airplane and tighten up an outer mold line, then use Kestrel and create a flyout model. Next natural step is put that into a flight simulator. Now, what you can do in a flight simulator on a backplane, you can have an avionics test bed, and if you have an open modular architecture, you can start looking at the interactions of the platform with the operation of the platform. In that backplane, that's where you start putting your threats, your radars, your sensors, and everything else. So now I'm in a systems of systems environment. But the forcing function on the front end is give me a paper airplane design, and I can get you into that environment. That's also, I think, where we'll be able to start in the future as we evolve in that direction. You can start looking at cyber attack surfaces. And this is pre-milestone A. Nobody's ever pushed the cyber sensitivities that far left. So I think that's kind of the enablers out there. But you have to open your lens and look at, okay, what can I do with this tool? And I think the simulators are the natural interface integrators of starting to look at systems of systems.
I wonder if our Lockheed Martin or Boeing reps would say anything about, since you each did comparisons to in-house codes, Were there problems moving between codes? Did you notice some major differences between the codes at all?
I'll take a crack at the first one. For Kestrel, there was a little bit more differences. In some of the garden variety, this flow is attached kind of thing. The agreement was very, very close with our in-house codes. When we start to look at some of these tactical fighters flying at high angles of attack, there were some differences, and generally, even the wind tunnel data was not a discriminator as to which one was really the correct answer. From the Helios side of the house, we're still looking at the same kernel of CFD solver. So if there was a difference between a solution that we got with Helios and one that we got with pure overflow, then that alerted us to that there was some sort of input error that was different between the two. But otherwise, what we found was oftentimes the Helios just gave us a cleaner workflow to get to the final solution quicker.
Just in regards to the F-35 solutions that we looked at, I showed one particular case with looking at one turbulence model in Kestrel. Actually see probably more variation as you switch turbulence models. We looked at SST and other models. There's a high sensitivity on that particular case to the turbulence models. So what we found in terms of comparing Kestrel to some of the other codes that we use, it's a very capable code. The numerics are similar. Some of the discretization and limiters are a little different, but we get very similar results.
Great, thanks. All right, this is a slightly different question, but a really important one, and that's how is the technical support for the CREATE tools managed, and how do you find the right balance between investments for development and support? I mean, are you providing enough support to this as well?
Yeah, so we, from the very beginning, we had established a quality assurance group. They're charged with, protecting the brand. Nothing goes outside of the program unless it's independently tested by that group. There's a healthy tension that exists between the development groups and the QA group, because the QA is, they truly are independent. And so when there are issues, then they'll resolved internally and then released. So in terms of protecting the brand, then we think it's just critically important that we have really good technical support for anybody within DoD or the stakeholder organizations that are using the tools. And so we have online services, so you've got online helps. As soon as you are granted access to the tools, you also have online access. So you can look at our online forums. We have online facts. You can submit questions and issues online. Our QA group also publishes their phone number and they answer their phone. And so we have an issue coordinator that triages the issues that come up and ranks a priority. The QA group then looks at differentiating it. Is this a bug or is this a user error? And if it's both of them are really important. If they're user errors, then that means our users guides, our tutorials, our trainings maybe need improving, and we do that. And we got just worth gold from the feedback we got from Boeing and Lockheed to feed back into our training materials and training programs. If it's a bug, then the QA's job is come up with a reproducible instance of the problem. The customer probably won't be able to share the actual problem at hand, and so we have to reproduce the issue. And then we give it to the developers to close it out.
Yeah, I guess one of the keys, and I think that was mentioned in the early charts, is that, I mean, certainly you have the domain experts, but you also tried to bring software engineering experts into this too, to engineer this code correctly, to work and live for 35, 40 years.
Yeah, the QA role is just critical to software engineering and software development. When you're a developer, you think very deep thoughts about very narrow subjects, and you want to unplug your phone, close the door, don't bug me, I'm busy. And that's great for the developer. So the QA person, they field all this. The developers don't want to have their time fractured that way. So our QA group interacts with the user community. They field these questions, and then we can pick our moments with the developers. And only when it's a bug, or we're highly confident it's a bug, then we can kind of hit them that way.
Yeah.
And then for usability features, we collect those and then provide them to developers, and then their regular software engineering development cycles. Scott, you're what, 2 weeks, 3 week? 2 week works sprints. So Scott takes these and builds work packages and puts them in the right sequence and gets them hammered out in the dot release or the general release.
Okay, great, thanks. It looks like we're getting close to the lightning round. We've got about 9 minutes and about 20 more questions to go through. Probably won't get to them all. Here's something people are a little afraid of, and it says, it seems like DoD will come to the point to recommend or enforce that CREATE be used to win contracts. Is that what you're seeing?
No, the government can't force
Right.
anybody to do anything. Just from internally, these are the tools we're using.
Right.
And if you want to use them, fine. We would, to change a paradigm, it's really important that, bigger than CREATE, that physics-based simulation and high-performance computing is, that's being used. We want to reduce the design cycles and time to deployment. That's the goal.
Yep.
And if
Yeah, we
CREATE
feel
helps.
though it's a really good idea though for DoD to understand for industry to understand what DoD is going to tell us. I mean, it's
Of course.
just a benefit to us. Now we would be really concerned if you had the CREATE AV tools and didn't share them.
Right.
Yeah.
That would be a problem. Yeah.
Right.
I would say that there is a concerted push to put in the contracts deliverables of the data necessary for CREATE tools.
Uh-huh.
So the inputs needed to run the CREATE tools.
So that if the government
You're
wants to
going
run
to
this
see
thing-
that in contracts of the future.
Yes, yes.
Is to be able to own the technical baseline. Allow us to be able to do this analysis and not be in the dark on the
Sure.
CAD and structural models and things like that.
Okay.
Yeah, there's another piece of that puzzle that
Please.
Scott referred to, and when he showed you the architecture, there's a module that you can plug in there that industry can bring their favorite flavor CFD code or their in-house turbulence models, whatever, to that architecture. So it isn't the one-size-fits-all for everybody.
Yes.
It's an architecture that's convenient for everybody, but it doesn't say you have to use KCFD.
You can
to
still
do
bring
it.
your special sauce,
Bring
your
yours in,
special code
yep.
to the game if you want. Yes, okay. CREATE supercomputers, as was pointed out, are accessed from a nationwide network, the DREN. Is cybersecurity a major concern for this program?
Yeah, the Defense Research and Engineering Network is one of 27 different Defense Department operated networks. It's in the top 3 of cybersecurity ratings. It's one of the most secure networks in the Department of Defense. Their number of incidences is fairly low, although no one is perfect. A key part of that is they're a very special purpose network designed to support high bandwidth, high speed data networks point to point for something like 300 sites. They don't try to provide the general class of computing network capability needed by the Defense Department at large. So they keep their job jar fairly narrow and fairly restricted to just this particular market, and their record is pretty good.
Okay. How about this? I'm merging 2 questions together here. Can the CREATE tools link to mission models to assess operational utility, or can they link to system architecture models to explore system architectures as well? So how do they link to other higher level models?
Yeah, the answer to both of those, yes. I tried to refer to that on the very front end when
Yes.
you're doing AOA studies, and you would use DaVinci in that. You can absolutely rip through the entire design space. Now, something to think about, once you've done that for a configuration like a cargo transport or a tactical fighter, you basically have all design sensitive parameters for that design. And you can just start to do a statistical analysis. Now, every one of those design points you can map into an engagement model. We've done that. So now I can run different scenarios with different design configurations and mission threads. For example, we did a design study on a next generation cargo transport. What would a CONUS lift to Middle East, CONUS lift to the PAC Rim, or a Asian relief thing? Those are scenarios. And then you get into all the combinations of design variables. How many times would I have to refuel? How many tankers would I need, et cetera, to meet that mission? And the other neat thing is then also, you can map every single combination of design points, which are now in response services, to cost estimating relationships based on traditional weight and other parameters. So I've given you mission utility, feasibility, and affordability. So that's the changing game that these tools are bringing to the table.
All right, all right. Is CREATE validated or certified by the FAA?
As far as I know, no. As we talked about previously, we have our own rigorous internal V&V activities, but Boeing and Lockheed, before they put it in their toolbox, they would go through their own validation process themselves. I think there is work to be done, broader than CREATE, though, with FAA and the DoD equivalents to define processes and acknowledge the role of physics-based sim in those processes.
There is a point that's maybe not appreciated quite so much. With the CREATE tools, you can get, with the SIDPAC models, you can actually get flight data for operations you would never take a real airplane through, operations near and beyond the safe operating envelope. And I've seen news articles where the FAA claimed if they had such data to train their pilots, they could perhaps make a significant reduction in the number of accidents. And so, not that just the CREATE tools would be the only ones that could do that, but that kind of data for pilot training would be extremely useful, particularly for the Defense Department, since they're more likely to put their planes through operation nearer the safe operating envelope, the edge, beyond.
So here's a question that's been rising, and it's kind of a tongue-in-cheek question, I think. I'm just going to read it. President-elect Trump has said that no computer is safe, and it is best to go with a note and courier system. I know you work a lot on user interfaces. Do you have a note and courier interface?
Well, this reminds me of L.F. Richardson back in the day of having an auditorium full of computers, and they each have their paper and pencils and share information back and forth by paper. That maybe that's an approach.
An old sneaker mail days.
So this may be the last question, and you did talk about it a little bit, but a lot of people are interested in hypersonics. And you did mention that, based on your resources, you stayed away from hypersonics in the first versions of all this,
right,
but that you're getting into it now. Can you tell us a little bit more about expanding Kestrel into hypersonics?
Yeah, I think the way to couch it is that we're building a collaboration between research, the basic research, AFOSRs, over and those kind of organizations, the AFRLs and Navy version and Army version, and CREATE to transition what has been out there in hypersonic research all these decades into a user production-oriented tool.
Okay.
That's what we're after, and so we're building that collaboration. We're even doing it here. We've got some meetings here where we're going to be working with those three entities to try to pull this together. And so our first step is to build a team. So we're adding subject matter experts in hypersonic area this year. And we have a plan to add chemistry and ablation and aerothermal structural interaction, all those things over the next few years, and then begin expanding that capability over the years. We will try to target parts of the hypersonic envelope that are easy to get to early, and then grow into the sustained hypersonic kind of area where it's full thermal soaking and things like that. But we're going to do it in a smart way, but we're going to do it in a way that keeps our research programs healthy.
Yes.
We're not here to take anything from them. We're here to transition them.
Yes, yes.
And make it so that the users can run the tools without having a PhD in a hypersonic field. We want them to be able to, we want to take the difficulty of running the simulations out of the picture, but transition all this excellent work that's been going on over the last couple of decades into this kind of a tool.
Okay.
So, yeah, that's kind of the thing. And we've got a 3-year plan, a 5-year plan, a 10-year plan, and we're working it. So.
Well, as we close, is there any last-minute comments that anybody would like to make on the panel today? Anything they wanted to say that didn't get asked right or something?
Well, I would just like to echo what Brian had in his talk about, so easy to see the value of a piece of hardware, a new machine or a wind tunnel model, and and just you can't see software.
Don't I know?
And what Doug was successful in getting on the table and what has been sustained by the HPCMP over
Yes.
time for modernization of software, in addition to their hardware networks, I think is I haven't seen it anywhere else. It's really, really remarkable.
Yeah. And I do remember what Andreessen said, software is eating the world. That really underneath almost all businesses, software is powering it now in so many ways and bringing innovation into the system. Well, on behalf of everybody, let me thank the panel here. It was a really interesting panel. I know it's a teaser for all the other CREATE sessions that are yet to come, and I encourage everybody to look through the program and find a good CREATE session to go to. Thank you very much.